This flowchart was designed to help you write chemical formulas for various compounds. We will look at each section separately and review how to use the steps to write formulas for binary ionic compounds, ternary ionic compounds, and binary covalent compounds. A binary ionic compound is one that contains two elements. The two elements must be a metal and a nonmetal in that order. We have already learned how to write the formulas for binary ionic compounds, so this will be a review. The first thing we need to do is write the symbol and the charge of the metal, which is the cation. Then we're going to find the symbol and the charge of the nonmetal, which is the anion. I will demonstrate this with the first example, which is calcium bromide. So calcium symbol is Ca. You're going to use your periodic table to find that symbol. And hopefully you have written the monatomic ion charges for main group elements on your periodic table. And we know that calcium forms a positive 2 charge. It wants to lose its 2 valence electrons. Bromide is the nonmetal bromine. We're going to look up its symbol on the periodic table and its charge as well. Remember that bromine has 7 valence electrons and it wants to gain 1. We're then going to look at the charges. If they are the same, we will drop them and bring the symbols together. But if the charges are different, we will drop the charges and crisscross the numbers to the bottom as subscripts, like as follows. We will rewrite the chemical formula, getting rid of the charges and leaving only the subscripts. We typically do not write ones when needed as a subscript, so my final answer is in the box. One thing that we need to make sure of as we leave this example is that the ratio of calcium to bromine, which is 1 to 2, is in its most simplified form, and in this case it is. If it was not, we would have to simplify the subscripts. At this time, I would like for you to try the 4 remaining problems. Go ahead and stop this presentation, and then when you turn it back on, I will quickly go over the remaining answers. So starting with aluminum oxide, you will find that its symbol and charge is capital A, lowercase l, plus 3. Oxygen is O minus 2. Those two charges are different, so we are going to drop the charge and crisscross the numbers down. We will end up getting Al2O3. A 2 to 3 ratio is the most simplest ratio. In our next example, lithium fluoride, you see that the charges this time are the same, a plus 1 and a minus 1. They will cancel each other out in a 1-to-1 ratio. We will end up with LiF. For calcium nitride, the chemical formula for calcium ion is Ca plus 2. For the nitride ion, it's N minus 3. Those two charges are not the same, so we're going to drop the charges and crisscross the numbers down to get Ca3 and 2. And our last example, potassium is plus 1, sulfur is minus 2. Those two charges are not the same. We're going to drop the charges and cross the numbers down. This crisscross method is a shortcut technique to get the ratio that will make the ions cancel each other out. One thing to remember is that all ionic compounds are neutral. They cannot have any charges in them, and that's why that crisscross method helps us come up with the ratio that will neutralize out those charges. The last set of examples that we did dealt with binary ionic compounds with type A metals. Recall that a type A metal only has one particular charge, whereas in this example, we will be focusing in on binary ionic compounds that are composed of type B metals. All the transition metals, with the exception of zinc, cadmium, and silver, fall under the type B category. In addition, both tin and lead are considered pseudo-transition metals. In these examples, you will see a Roman numeral behind the metal name. That is to signify that the metal is a transition metal that has more than one charge, and you will only use the charge that is seen in the parentheses as a Roman numeral. Remember, all metals have positive charges. So once again, following the rules in the box, we're going to write the symbol and the charge of the metal, that is, and then of course the charge is what is seen in the parentheses. So we will take Fe, the Roman numeral 3 tells us it's a positive 3 charge. Chloride is chlorine. We will look up its symbol on the periodic table and its charge. And once again, if the charges are different, we're going to drop the charge and we're going to crisscross the numbers down, and we will rewrite the formula without the charges. At this time, I would like for you to stop the presentation and try the next 4 examples on your own, and then come back and you will see the answers presented to you. In our second example, we will be looking at copper 1 oxide. Copper has a charge of +1. Oxygen is O-2. The two charges are different, so we're going to drop the charge and cross the numbers down. Remember, we do not write ones as subscripts. In cobalt 2 nitride, cobalt's charge is +2. Its symbol is CO. Nitride is nitrogen and -3. The two charges are not the same. So once again, we're going to drop the charges. We're going to crisscross the numbers down. And we're going to write the ratio of 3 to 2. For yttrium 1 oxide, yttrium's charge is +1. Oxide is oxygen with a -2 charge. Once again, we're going to crisscross those numbers down because the two charges are different. And lastly, we'll take tin 4. Remember, tin is a pseudo-transition element. You know that it has multiple charges because of the Roman numeral 4. So tin is +4. Sulfide is sulfur S-2. We're going to go ahead and crisscross these down. We're going to get SN2S4. Remember the caveat about doing the crisscross method? We want to make sure that the ratio is in its simplest form. If it is not, we do need to rewrite it in its simplest form. When I crisscrossed the 2 and 4 down, I got a 2 to 4 ratio. I can simplify that, and I will do that, and this becomes SNS2. That is the correct answer. The next set of compounds we will write formulas for are ternary ionic compounds. What makes these different is that there will be at least 3 element symbols in the chemical formula, which means that a new type of ion will be introduced into these formulas. They are called the polyatomic ions. To the right, you will see a list of polyatomic ions. You can find this list on your reference sheet. I want to take a moment to go through and explain what you are seeing on this list. So polyatomic ions are groups of atoms that act as one piece, one entity, with a single charge. If you just see pluses and minuses, those are actually +1 or -1, and you will notice that most of the polyatomic ions do have a -1 charge. There are a few that have -2 charges, and there is one that has a -3 charge. So most of the polyatomic ions are anions, which means they are going to be found in the back half of the compound. There is, however, one positive polyatomic ion, and that is ammonium. Since ammonium is a positive ion, it will be found in the first part of the name if it is being used. Lastly, I would like for you to notice that most of the polyatomic ion names end in -ate and -ite. There are 2 that actually end in -ide, and we need to be careful about recognizing them as polyatomic ions. They are cyanide and hydroxide. To write these formulas, we will do pretty much the same thing we've done with the last 2 sets. The only difference is we will put a parenthesis around the polyatomic ion when present. We will remove that parenthesis at the end if it is not needed. It will not be needed if there is a 1 on the outside of the parentheses, or you did not use crisscross. I will explain when we get to an example that reflects this. So let's start off with magnesium sulfate. Magnesium symbol is Mg, and it has a charge of +2. I notice that the back part of the name is ending in 8, and that tells me that I'm going to be looking at the polyatomic ion sulfate. So according to the chart, and I'm going to wrap it in parentheses, it is SO4 minus 2. So we know that if the charges are the same, we're going to drop them, and we're just going to bring the symbols together. And when I do that, I'm going to get MgSO4. Notice that I removed the parentheses because it was not needed. There is only one magnesium and one sulfate ion in this chemical formula. Go ahead and pause this presentation and try the next 4 on your own, and then come back and check your answers. Alright, welcome back, and let's take a look at calcium, which is Ca plus 2, and the hydroxide ion. Remember, the hydroxide ion is OH minus 1. Those two charges are not the same, so I'm going to go ahead and drop the charges, crisscross the numbers down, and when I rewrite this, I'm going to get Ca parentheses OH2. That parentheses is needed because it reminds us that for every 1 calcium, we need 2 of the hydroxide ions to neutralize out the calcium's charge. In our next example, we have sodium, which is Na plus 1, and nitrate, which is NO3 minus 1. Once again, I'm looking on the list, and I will see that nitrate is NO3 minus 1. Those two charges are the same, so all we have to do is drop the charges and bring the symbols together. In this case, we would remove the parentheses because there is not more than 1 nitrate needed to neutralize out the sodium's charge. In our next example, you'll notice that the polyatomic ion is no longer in the back of the compound, but it is located in the front of the compound. So we would look up ammonium on the chart. We would get the chemical formula of NH4 plus 1. Notice that the nonmetal in the back is not a polyatomic ion. It is ending in "ide," and it's not hydroxide or cyanide, so it is chlorine with a -1 charge. And once again, these two charges are the same, so all we're going to do is drop the charges and bring the two chemical symbols together. Notice that I removed the parentheses because for every 1 chloride ion, I only need 1 ammonium ion to neutralize it out. And last but not least, this is an example where I actually have 2 polyatomic ions in my name. I've got the ammonium, which we just learned is NH4 plus 1, and that 8 is reminding me that it is also a polyatomic ion, and that is CO3 minus 2. Once again, those two charges are not correct, so I'm going to drop the charges. I'm going to cross the numbers down, and in this case, I will keep the parentheses for NH4 because more than 1 is needed, but I will lose the parentheses for carbonate because I only need 1 carbonate to neutralize out 2 ammonium ions. The last set of formula writing that we will do will be for covalent compounds. Recall that covalent compounds are between non-metals. We will also only be writing formulas for binary covalent compounds. That means we will only be looking at compounds that consist of 2 nonmetals. Remember that there are no ions present in a covalent compound because the valence electrons are being shared, not transferred. If you take a look at the rules for writing formulas for covalent compounds, the first step will be to write the symbol for the first nonmetal and use its prefix to correlate to a subscript. That subscript tells you how many of those nonmetals will be in the chemical formula. We will then write the symbol of the second nonmetal and once again use the prefix to represent a subscript for that nonmetal as well. It's very important to remember that when we write these formulas, we do not simplify. So let's go ahead and get started with the first one. I see carbon as my first nonmetal, so I'm going to simply write the symbol C. The second nonmetal is the oxide portion, which is representing oxygen, which is O. And you can see that the prefix mono is in front of it, and that represents 1. So my chemical formula is capital C, capital O. For the next one, I have diarsenic. So I'm going to use the symbol for arsenic, which is AS. The prefix di represents the subscript 2. We've got oxide, which once again is oxygen. And the prefix 3 represents that there are 3 oxygen atoms. In our next example, we have sulfur, which is S. And then we have oxide again, which is O. The hexa means that there are 6 of them. In our next example, we see a prefix of di on the element name nitrogen. So I know that nitrogen symbol is N. Di represents 2. Hydride would be the nonmetal hydrogen. And tetra means 4. And lastly, dihydrogen. So hydrogen is H, di is 2. And we have oxide again, oxygen, as our second nonmetal. Mono means 1. And hopefully you recognize that H2O is water. So the official name for water is dihydrogen monoxide. Notice that we are not going to simplify any of these subscripts in the chemical formula. Now that you have learned how to write chemical formulas, we are going to do the opposite and learn how to name chemical formulas. Just like before, we will use this flowchart to take you through specific steps on how to name binary ionic compounds. Remember, those will be between metals and nonmetals where only 2 elements exist in the compound. The metal can either be type A or type B. Ternary ionic compounds, where we will most often see that there is a metal paired with a polyatomic ion. Sometimes we'll see the ammonium ion paired up with a nonmetal, and occasionally we'll see 2 polyatomic ions paired together. And then the covalent compound that exists between 2 nonmetals. In this next set of examples, we will be looking at ternary ionic compounds. Ternary ionic compounds will consist of 3 or more elements in the chemical formula, and that indicates that a polyatomic ion will be present. Since most of our polyatomic ions are negatively charged, most chemical formulas will have the polyatomic ion sitting in back, and we will generally see a basic format of the metal paired with a polyatomic ion. But there will be scenarios where we might see the only positive polyatomic ion, which is ammonium, paired with a nonmetal, or that ammonium ion paired with another polyatomic ion. How do we locate the polyatomic ion? The biggest indicator of a polyatomic ion is a parentheses. Inside the parentheses will be a polyatomic ion. So if we take a look at example 2, you will see that OH is in parentheses. That is the hydroxide ion. And if we take a look at example 5, you will see that NH4 is in parentheses, and that is the ammonium ion. If a chemical formula does not have a parentheses, then we would look for 2 capital letters sitting next to each other. So in our first example, you can see that in the back we have capital S and capital O, and if we come on over to the reference sheet, you will see that that correlates to the sulfate polyatomic ion. In the third example, we have in the back again 2 capital letters, N and O. Of course, there are 3 oxygens, so we're going to look on our polyatomic ion list and find NO3, which is nitrate. And in the fourth example, you can see 2 capital letters sitting in front. That's NH4, that is our ammonium ion. And then in our fifth example, we also have 2 capital letters sitting next to one another, not in parentheses, and that is the carbonate ion, as you can see over here on the list. So if the polyatomic ion is in the back, we will write the name of the first element, which is the metal. So if we take a look at our first example, the polyatomic ion's in the back. We're going to write the first element's name, which is magnesium. Remember that metal can be type A or type B. In this case, it's type A. So we do not have to do anything special to it. We're just going to write the element name. And then we go to the list and we look up the name of SO4, and that is sulfate. The only time the subscripts in the chemical formula are important to the name is if we are looking at a substance that has a transition metal in it. The second example also has the polyatomic ion sitting in the back. So I'm going to go to the first element, which is a metal, and I'm going to write its name, which is calcium. It is a type A metal, so I don't need to do anything special to it. I'm then going to look up OH on the list, and you will see that it has the given name of hydroxide. My third example follows the same pattern. The polyatomic ion's in the back. That means that what's sitting in front is my metal. My metal's name is sodium. Once again, it is a type A metal, so I don't need to do anything to it. I'm going to go to the list. I'm going to look up NO3 minus 1, and you will see that it has its given name of nitrate. In the next example, you will see that the polyatomic ion is sitting in front. So polyatomic ions have special names. NH4 plus is called ammonium, so I will write that in. And you will then see what is left over is just a nonmetal. So that nonmetal follows the same rules as before, where it ends in "ide." And in our last example, we have 2 polyatomic ions, so this will just be a name where we use both polyatomic ions. So NH4 is ammonium, and CO3 is carbonate. Once again, the subscripts have nothing to do with the name unless a type 2 metal was given to you. None of our examples included a type B metal, so let's do one last example. We're going to name the compound of FeClO2 3. So if I looked at this formula, the first thing I would notice is that there are 3 element symbols. I know there's a polyatomic ion present. The parentheses is going to help me identify that polyatomic ion. It is ClO2. And if I go to my list, I will see that that is called chlorite. So I'm going to name the metal, which is iron. Iron is a type B metal, so I'm going to put a parentheses behind it. And then I'm going to go ahead and name the ClO2 with its given name of chlorite. And just like before, I'm going to come up with the charge of chlorite, which is -1. I know that there are 3 of them, so that would give me a -3 total charge. I'm going to make that a positive number, and then I'm going to divide that by the subscript of the metal, and that would tell me that the charge of iron is +3, and I could write that in the parentheses. You can also use the shortcut. Remember that the shortcut is going to take the subscripts and cross them back up as charges. When we don't see a subscript, we assume it to be 1, and you can see here that the chlorite ion has predicted to have a -1 charge. We just did it the harder way, which tells us it did have a -1 charge. So iron would have a Roman numeral of 3 as a charge. This last set of examples will be naming covalent compounds. Remember that covalent compounds are composed of nonmetals. There are no ions present, so we simply use a prefix system to help us indicate how many of each nonmetal is in the chemical formula. Please remember to memorize these prefixes. And then the only other thing that you would need to remember in this set of practice is that even though one has a prefix of mono, we never use the prefix mono in the first nonmetal's name. So with that said, let's go ahead and do these last 5 examples. So if I look at this chemical formula, I'm going to notice that there is no polyatomic ion, there is no metal, which means it is covalent, which means now I'm going to use my prefix system to name it. We name the first nonmetal with its given name, which in this case is carbon. It does have a subscript of 1, but we never use the prefix mono in the first position. The second element is going to have its ending, which is oxygen, changed to "ide," but we do use the prefix mono for 1. And instead of saying monoxide, we just drop one of the vowels and it becomes carbon monoxide. If we take a look at the second example, once again, no polyatomic ion, no metal present. We know this is a covalent compound. We are only going to use our prefixes to represent how many of each nonmetal is in the chemical formula. So the first element is arsenic. The 2 has a prefix of di, so it is diarsenic. And then, of course, oxygen is going to end in "ide. And the prefix for 3 would be tri. So this is diarsenic trioxide. In the next example, I have sulfur. Notice I'm not using the prefix mono, even though there's only 1. And then 6 is hexa. And then once again, oxygen turns into oxide. In the next example, we've got 2 nitrogens, so that would be di-nitrogen. I have 4 hydrogens. The prefix for 4 is tetra. And then I'm going to drop off the suffix and add ide. A lot of students make a mistake here and they put hydroxide. Remember, hydroxide is a polyatomic ion, and O and H are connected to one another. So this is definitely not hydroxide, it is hydride. And then our last example, we've got di, hydrogen, and then we have the 1, mono, and instead of saying monoxide, we're just going to say monoxide. So dihydrogen monoxide. This concludes my presentation using the flowcharts to either name compounds or write their chemical formulas.
Please understand how important it is for you now to go into that practice packet and work through all of the examples that we give you. Make sure you have your reference sheet in front of you and these flowcharts. The practice packet has been broken down into parts. Each of the first 4 parts targets a specific type of compound. The last part is a mixed set of compounds. At that point, it will be extremely important for you to decide whether each compound is ionic or covalent, and then use the appropriate rules to get a correct answer.